Yeah, you can start.
Okay, very good. Well, thanks, Ahmed, for inviting me and for the opportunity to be there with you online. But I hope I'll meet many of you soon. Um, this is a great opportunity to talk about this recent work that we put in the archive in October. Well, first of all, can you hear me properly?
Yeah.
Okay, good. Well, I'm aiming for 45 plus 15 of questions, but if you have questions throughout, just interrupt me, feel free. And yeah, so I was saying this is some work that we put in the archive in October. Is the first work of hopefully a series of them. And this is a collaboration that I have with these nice colleges, Anju, Ratul, Anshuman, Francesco, and my supervisor, Fernando. And what I want to talk to you about today is string thermodynamics in and out of equilibrium, Boltzmann equations and random walks. So this is a very long title. There are several questions I would like to answer throughout. So can I change? Oh, okay, good. So let me give you a bit of an outline. Ignore all of these formulae. I just took the image from internet and I don't think they make a lot of sense. They are not in my paper. Okay, and the questions I would like to answer is, first of all, why is this interesting? Why should we be bothered to do this? And I will tell you, hopefully, I will convince you that string thermodynamics is very interesting, both from a formal point of view and a more phenomenological point of view. And as we will see, the Boltzmann equations are a very powerful tool if we want to study the out of equilibrium physics that inherently we should try to address. Then how can we do this? What are the building blocks? What is the setup? What is this thing we want to work with? So we will cover how to formulate what is a phase space formulation for string theory, at least in the most simple setups. And then we will see what are the quantities we need to compute in order to pose these Boltzmann equations, which are interaction rates for typical strings. And we will go ahead and talk what is a random walk interpretation. Now, of course, it's always nice to check. It's something you have to do. That's what does your work actually work. And we'll see that we have very good hints that what we've done is correct in the sense that we can reproduce known results from thermal equilibriums or from equilibrium string thermodynamics. And we will do this by the principle of detailed balance, which is going to play a very prominent role in today. And lastly, presumably the most important question when you finish a work is being able to answer what have you learned? What do we learn out of this? And we will see that we can infer what is a form of highly excited string interaction rates from random walk considerations. And we will also learn a little bit about non-equilibrium aspects of string thermodynamics. We will see that we can, in simplified setups, find analytic solutions for how the fluctuations behave. And in the more complicated ones, we will see that we can estimate very well the equilibration rates. Okay, very good. So let me start by the more formal sort of point of view. I'm going to show you a couple of very cherry-picked references in which, with some comments, which I want to use to illustrate my points, but this is, of course, not all the references in string thermodynamics, and I refer you to my paper if you want to check a little bit more. But the reason, or one of the reasons to study string thermodynamics is its formal aspects, because string thermodynamics is very different a priori than particle thermodynamics. And the reason is the following. At sufficiently high energies, Brandenberger and Baffa showed in the 89, so kind of long ago, that the density of states for a single string in any background that allows for a worldsheet CFT description reads in this way. And in particular, notice that the density of states grows exponentially with a characteristic scale, which is, of course, the only scale of the problem, root alpha prime or its inverse. And this exponential here is very interesting, because if I want to, with this density of states, compute the partition function, I need to compute this integral here. And it's clear that there is a competition between both exponentials, the Maxwell suppression, and that of the density of states. And if this change signs, this quantity here, can you see my cursor?
Yep.
Okay, very good. So if this quantity changes signs, the partition function diverges. So clearly something interesting is going on there. This is going to give us a characteristic scale where interesting physics happen. And this led to Attic and Witten to write their seminal paper, in which they mentioned, among other things, they mentioned that there's a similarity between this sort of Hagedorn phase in string theory, or essentially the consequences of having an exponentially growing density of states have been studied before string theory around the 60s by Hagedorn and friends in the context of what now we understand as strongly coupled QCD. So this bootstrap model for hadrons, as it was called, featured an exponentially growing density of states. And the analog of beta H in that case was what we now understand as lambda QCD. So they were studying the low energy physics of a theory that at high energies undergoes a deconfinement transition. Its fundamental degrees of freedom are revealed. So Attic and Witten asked the question, what if this is the case as well? Is there a phase transition hiding at these temperatures? If I manage to put string theory at these temperatures, will I be able to understand what are its fundamental degrees of freedom? It's definitely an interesting question, but I have to warn you, this is not a question I'm going to address. Here I just wanted to make very clear that there is this Hagedorn temperature, that this is an important quantity, and that the exponentially and that the density of states grows exponentially, and this will be important later. But I'm going to refrain myself from studying temperatures higher than the Hagedorn temperature. I'm going to remain below. Okay, so this is for the formal aspects. Now, from the more sort of pheno point of view, the idea is very simple. If I heat up a box of anything and I give it enough energies, string modes according to string theory will eventually be excited. So a natural question is, could this have happened in cosmology as the universe became very small if you do some sort of time reversal? And the answer you can check in this recent review in string cosmology is that maybe, because in string theoretical models of the early universe, you can find energy densities of further one string units. It's not uncommon, and even larger than that. So it is a natural question to ask, could this have influenced reheating? Could fundamental string degrees of freedom have had influences in reheating? Could they tell us something about the moduli problem? Most importantly, at least for me, this is what I'm working on at the moment. Could it assume this happened after inflation? Assume you have some sort of Hagedorn phase after inflation. Are there any imprints of this? Would they have released a gravitational wave spectrum? The answer is I don't know for the moment, but this is work in progress. I want to make a comment, though, that high frequency gravitational waves, so gravitational waves from the very early universe, are a topic that is attracting a lot of attention at the moment. You can check out this nice reference here. And again, a couple cherry-picked references for stringy effects in heating. Now, it's most likely that out of equilibrium processes are going to be important if I want to study cosmology, and more in particular, string theory. And for this, I'm going to use the Boltzmann equation technology. So why Boltzmann equations? As probably you know, but in case you don't know, they describe the evolution of a probability density in phase space, and they therefore provide an invaluable window to out of equilibrium physics because its regime of validity is larger than the equilibrium one. And it is very important that in situations in presence of gravity, we can understand what a little bit of the non-equilibrium regime, at least because of two reasons. First of all, gravity is dynamical, so you could have, fluctuations in your thermal plasma that under their own gravity collapse. And for black holes, this is the moral of the Jeans stability. But also in an expanding universe, it might happen that the expansion of the universe or the rate of expansion of the universe becomes faster than the typical equilibration rate of the particle plasma you're thinking of at the moment, and that it decouples, it falls out of equilibrium. This is what happens, for instance, with neutrinos in the early universe. So in order to address this, we would like to know about interaction and equilibration rates, so we can estimate when and whether equilibrium is a good approximation. And if not, we would like to have Boltzmann equations to understand what happens after we fall out of equilibrium. And that's about it for the motivations. I would like to talk about the building blocks where we are going to formulate these Boltzmann equations. But before, are there any questions on what I said? Okay.
Can
Sorry?
I ask?
Yes, of course.
You said that you can use this also to inflation, but what will be the difference between standard inflation, that is when you perturb the metric and then you quantize and find the power spectrum and so on, and the expect the correction induced by this string model?
Yeah, I'm not sure. I might have said something I didn't want to say. I am not thinking of applying this in inflation. I'm more interested in thinking, what if after inflation, imagine some sort of super energetic and violent preheating like process. Could this have excited fundamental string modes? Or after inflation, after Brane anti-Brane inflation, in principle, you expect cosmic strings or very highly excited strings to show up. So we would like to understand what are the consequences of this happening. But I do not have any concrete proposals on how to realize this within inflation or as inflation is happening.
Okay, so you say just after reheating.
I think that would be a nice, interesting place to look at. Yes. Although for the moment, all I'm going to do in this talk is going to be in flat spacetime. So I'm not going to assume expansion of the universe. I'm just going to pose the equations and find solutions to them in flat spacetime. The generalization to an expanding background is work in progress.
Okay, thanks.
No problem. Are there any more questions? Okay. So let's talk about the building blocks. How could I pose Boltzmann equations for string theory? Well, first of all, I need a phase space. And a phase space for string theory would look like something along these lines. If you allow me to consider a string in big D dimensional flat spacetime, in which little d of the directions are effectively non-compact, and when I say effectively non-compact, I'm trying to say that their typical size is much larger than the size of the typical string, which are going to be very long, they are going to be highly excited. If that is the case, then I can break down the phase space into usual position and momenta. Compact or non-compact is also shows up in ordinary particle physics, right? But I will also have winding and KK modes. Winding and oscillator modes. So if I write my favorite equation, E squared equals K squared plus M squared, I see that all of the degrees of freedom contribute to the mass, to the effective mass of the string. And if I know, if I know the tension of the string, which I'm going to assume, then I know its length. And henceforth, I will characterize the strings by their length. But the idea is simple. In principle, I need to describe the thermodynamics with a distribution in a generalized phase space, which takes into account all of these additional degrees of freedom. If the background is more complicated and there are more degrees of freedom, I would have to take them into account as well. But for the moment, I'm going to keep it simple. Now, please don't kill me if you're familiar with this, but I want everyone to be on the same footing. This is a toy model for a Boltzmann equation. I'm going to assume I have 3 species of particles of types A, B, and C, and only this process. So they transfer energy among each other so that A can decay into a pair of B plus C, or on the other hand, B plus C can merge into a particle of type A. And if this is the only process involved, then the Boltzmann equation for the A particles, for the phase space density of these particles, is going to have the 2 contributions. One is negative. It takes into account the decay of the particles. So it's proportional to the number of particles, or to this probability density of particles of type A and its decay rate times some quantum enhancement or penalization, which I'm going to be interested in at the moment. And then there is going to be an additional positive term, a term that creates particles of type A, which is through the inverse process of B and C merging. So it's proportional to the probability densities of B and C and to an interaction rate. And the reason I'm writing this, I know it's very simple, but it very nicely illustrates the physics of what's going to happen later when the equations become horrible. So in our sort of stringy phase space, which we were considering a contribution to F of L, would look like this. I need to sum over all possible quantum numbers that can give strings of this particular type. I need to integrate over all non-compact variables as well. And at this fundamental level, at this sort of primitive level in which I'm working with the phase space distribution, the amplitude of the process factorizes by crossing symmetry, and I get this integrand here. So this looks very horrible because there are many contributions, but it is very easy to find equilibrium distributions. And the reason is because of the principle of detailed balance. You could think of 2 ways of imposing thermal equilibrium. You could say that dF dt must be 0, or you could say that there is not energy inflow between different channels. Both statements are equivalent, and it's very easy to see this here. The way to make dF dt equals 0 is to make this term in brackets 0 and then, this is one process, and I'm summing over all possible other processes. So I'm going to make the process cancel out channel by channel. And this is the principle of detailed balance. What is the solution to make that 0 is, of course, our very well-known Bose-Einstein/Fermi-Dirac statistics. And at fixed K, if I want to take into account the density of states, this is what the equilibrium distribution looks like. And I'm going to put this in my pocket and use it afterwards to compare with already known results, because I'm going to find something very similar to this. Okay, So that is how detailed balance works, and we're going to use it in what comes. Now, if I want to pose Boltzmann equations, I need to compute interaction rates. And this is in principle very difficult because, there is one of these rates per process, and there is an exponentially large number of processes because there is an exponentially large number of strings. Plus, they are very difficult to compute, so it looks like we're in trouble if we want to pose Boltzmann equations for this quantity. So what we are going to do instead is to ask the question, okay, what if I try to pose Boltzmann equations for the typical string or the average string? And it turns out that that is a problem that can actually be solved. That is, you can handle it. And the way to do so is to consider this very weird looking process in which it's called the average semi-inclusive decay rate. And what I am studying essentially is take a string, fix the level of the string, and ignore any other of its attributes. So at fixed level, average over all possible strings within that level, and let it decay into this pair of strings. One whose state I know very well is described by a vertex operator V1, and another one which looks like the former one. I know its level, but nothing about its particular state. And this looks weird, but you will see in a moment that it is actually helpful. If I want to compute this decay rate, I need to do something along these lines. Sum over all possible final states, average over all possible initial states. This calligraphic G is going to be the number of states within a level. And if you are able to perform these computations, you are done. And we actually can do this. The reason is that if I insert projectors here, I can write the expression as a trace. And traces are something that we know how to do in string theory. So I compute the trace, then project, and find my decay rate. This was done, or something along these lines was done first, as far as I know, by Amati and Russo in the 1990s, which they specified the vertex operators for massless particles, went to the large n limit, and what they were doing essentially was studying the radiation emitted for a typical string. We're going to do something similar, or Mañez did something similar a bit later, and he managed to compute this amplitude for an arbitrary vertex operator. And what he found is that you can break the contribution into two parts. This one, which I will tell you a little bit more about in a second, but you can see it's universal in the sense that it does not depend on the particular vertex operator V1 I was considering. It only depends on n prime, or n2 as I was calling it, and the mass of V1. So this would be analogous to n1. So there is this contribution and a non-universal contribution, which is dependent on the vertex operator, but in general much smaller than this one. So we are going to focus in this universal contribution, and then because it's the same for all vertex operators within a level, I'm going to sum over all states within that level, and I'm going to find the typical decay rate. So how a typical string decays into a pair of typical strings, of which I only know the level. Because these are typical configurations, then it follows that what is the maximum or the typical decay is going to dominate the ensemble. So from these considerations, we're going to be able to understand how the typical string looks like. And it is for this quantity that we are going to pose Boltzmann equations, for the typical strings, for the distribution of typical strings in in an ensemble. I heard some noise. Was there a question? Sorry if I talked over.
No, I don't think so. But
Okay, good. Okay. Okay. So as I was saying, if I consider the typical decay rate, I'm going to understand the typical string, how it looks like. And it turns out that the typical string prefers to release energy into oscillator modes, and therefore the typical strings are non-relativistic and its decay approximately preserves mass. The reason for this is simply that there is an exponentially larger number of oscillator modes. So there are many more modes to release the energy into. But what follows from this is that the typical string is described by its length, and that the typical interaction preserves length. And we will use this later.
so
Now,
Yeah.
yes.
my question. So typical, you have somewhere to put some statistical measure, like all states are equally probable or something like that. I mean, how can you get a typical string out of nothing? I mean, there must be some underlying assumption.
So it is true that, you know, imagine I fix a level, all microstates have the same probability,
Okay.
but then the macro state, which I characterize only by its length, and, you know, as we will see, the decay rate of the string looks it admits a very semi-classical interpretation. And the semi-classical interpretation has to do with its shape. What I hope to convince you about is that there are some microstates, for instance, the one in the, the one with maximum angular momentum is a closed string that simply rotates. No, it's a circle that is rotating. But there are very few microscopical configurations that give you these macroscopics. Instead, the strings look like random walks. And the reason is that there are many microstate configurations. There are many vertex operators, if you want, that give you this sort of shape.
I see.
Does this answer your question?
Yeah, that absolutely answers the question. So you're just saying I'm fixing the level. How does the string look like? Well, since I'm assuming that all the microstates in this level are equally probable, so I'm just gonna look for the most probable types of configurations under that.
Very good. Exactly.
Yeah. Okay.
Exactly. Yeah, thank you. That was a very nice summary. This is exactly what I'm doing. Okay, so this is what the decay rate looks like. What I have for open strings within a brane world, I'm assuming I live in a D25 brane because this is bosonic string theory. I will do better later. But at this point, this is what the typical string wants to do. Its decay rate is not dependent either in its length or the length of the product. So the semi-classical interpretation of this is that the string is traveling and it can break. It could break through any of its points with equal probability. The brane can break the string. For the closed string, this is a bit more complicated. We have this very weird looking factor which admits a random walk interpretation about which I will tell you in a moment. But the semi-classics, just keep this in mind. What's happening is that the string needs to touch itself in order to break. And this is measuring the probability for that to happen. Okay. As I was saying, we will use random walk arguments to infer decay rates for more complicated setups. But let me remark that this has been computed in the worldsheets. And all the approximations I've done, I've told you. And you can find them in the paper, in the nice paper of Mañez. With those, we can at last set Boltzmann equations for a soup of strings. In the simplest case, in which all the typical string is much larger than all the directions, this was done already. And we've generalized it to find this sort of equation. So let me first tell you what's going on. As a recap, what we wanted to do is to describe the thermodynamics in terms of the typical string, of how the typical macroscopic configuration looks like, which as we saw is well described by the length and by the number of non-compact directions. So using the interaction rates we've computed earlier, we can pose a Boltzmann equation for this sort of strings, where n is the number of strings with lengths between L and L plus L. So this is the first moment of the probability density for aficionados. And now it's not obvious that detailed balance happens because I've performed sums, I've done averages. So it is not completely obvious that if I make this integrand 0, it will happen throughout all of the lines. But it is the case. I'm gonna walk you very quickly through the equation. This is an equation for the number of closed strings with length L. And I need to sum over all possible processes that involve shorter strings and longer strings. For the shorter strings, there is a positive contribution in which strings of lengths L prime and L minus L prime merge into each other to give me a string of length L. And the opposite case, which is my string decays into that particular pair. And similarly, regarding interactions with strings that are larger, a larger string could break into a pair of which one has length L, and in the opposite process, any string could absorb the string of length L to form a string of length L prime. So at this order, these are all the possible processes, and you can find an equilibrium distribution by imposing detailed balance with, at this stage, is not obvious, but you can do, and this is the equilibrium solution. So it looks somewhat what you would be expecting. There is an exponential suppression, but you have to be careful because this is not a temperature. And the reason is that, as I was saying before, this quantity must be multiplied by a density of states. Its shape must be a density of states times a Boltzmann suppression. So you need to identify this 1 over L, which in our setup shows us an integration constant with a difference in inverse temperatures. And as I was saying, this disagrees with general considerations in equilibrium thermodynamics if you take into account all the degrees of freedom involved carefully. Okay, those are the equations, but we would like to do a little bit better. We would like to include open strings. What happens if my branes have a dimensionality that, if my branes are not space filling? And the way that we found to go forward is to use random walk arguments. So just a little crash course on random walks. The idea is that highly excited fundamental strings, or the typical configuration of a highly excited fundamental string, forms a random walk, which is a n-step path on a d-dimensional lattice where the direction of each step is taken at random. The important part, really, the important fact to keep about this is that the probability of a random walk of n steps, which in our language is length L, to come back to its origin is 1 over n to the d over 2, where d, remember, is the number of non-compact directions. So now I can give you a little bit of an explanation for this factor here. The semi-classical analysis is telling us that there is a factor of L, because my closed string could break through any of its points, and fixed a point L, say this one. There is a probability of 1 over L to the D over 2 that it closes in this side because it forms a random walk. There is a probability of 1 over L, big L minus little l to the D over 2 for it closing in the other side. And of course, these probabilities are not independent because the random walk was already closed. And this is my other factor of big L. This is the interpretation. And with this nice simple interpretation, we can argue what is or what should be the shape of much more complicated rates, such as this one. This in here, what I'm picturing is an open string of length L that is probing one of the directions transverse to the brane, and it breaks up. It finds a piece of itself at some point, and it breaks into a closed and an open string of these lengths. And one can argue through random walk arguments. I'm not going to bore you with it, but one can argue that this is what the interaction rates should look. These are very complicated. We have not been able of doing a worldsheet analysis of this, but if any of you is interested in this sort of hardcore worldsheet computations, this is a challenge for you. The moral of the story is that the rates should look pretty much in this way. And the reason why we think we are right on this is that these interaction rates satisfy detail balance. Let me show you, just skim through that. What happens if I add D-branes is that I have two populations of strings now. These are there are closed strings with a Boltzmann equation. There are open string with a Boltzmann equation. These equations, all of them look horrible, but and I am allowing for energy transfer between both sectors. And the magic of detailed balance is that I can very easily find an equilibrium solution just by making any of the lines to be zero. If I set one of these lines to be zero, if I impose equilibrium in one channel, then equilibrium among all channels follows. Make zero one of these lines, and all of the lines will be zero. So you find equilibrium distributions very easily if you identify the right channel and its inverse. We can go further. We can allow the open strings to probe the transverse directions to the branes, and everything looks horribly difficult and complicated, but the moral of the story still follows. If you make one of these lines zero, all of them become zero. And of course, the phase, the density of states you find from these considerations agrees with what you could find from state counting. Okay, so that's about it for equilibrium thermodynamics. I will tell you a little bit more in these 10 minutes about non-equilibrium, but before that, are there any questions?
Yeah. So in the beginning you had winding also.
Yes.
Was the winding present in these last formulas or not? Because
very good.
Then I have a hard time seeing if you have a large compact dimension, the probability for strings, unwound strings forming wound strings, and how it depends on the radius of the dimension and so on. And of course, eventually finding some more precise argument than the one of Brandenburger and Baffa for four-dimensional non-compact dimensions and the rest of them compact.
Very good. In this setup, I have not considered winding, but the reason is that in order to find these equation here, remember in the beginning I was summing and taking averages. I've summed here over all possible winding modes in the compact directions, in the effectively compact directions, and I'm assumed I cannot, I have not summed over those in the non-compact ones. So I'm assuming I have zero winding along the non-compact directions, and I'm summing over all possible winding states within the compact ones. So this typical string also takes into account winding along the compact directions, and it does not wind along the non-compact ones. Does this make you happy?
Yeah, partly, but how about 4 dimensions?
4 dimensions you get from here. For d equals 3, you have 4 dimensions.
Thinking like a probability argument. So you start with the universe where everything.
Brandenberger buffer. Yeah, of course. Of course. No, I don't think I have anything at this level to say about that.
Okay.
Sorry.
Okay.
Yes. I would love to though. Yes, of course. Yeah. No, at this level we don't have anything to say about the Brandenberger buffer for the 3 + 1 dimensions.
Okay.
Okay, are there any more questions? Okay. So this was all very nice, but there is not much we've learned at this point, because we were just reproducing the results from equilibrium thermodynamics in a horribly complicated setup. What we win from Boltzmann equations is that we can probe the out of equilibrium regime. In order to do this, the strategy is going to be the following. Consider your equilibrium distribution, do a small perturbation, and study the resulting Boltzmann equation at leading order. This is how the story looks like in little d equals 0. So in the simplest case, in which all of the strings are much larger than the typical size. This is the evolution at first order for this fluctuation. And I've made a little bit of progress because at least the equation is linear, but still integral differential, so it's still very complicated. But nonetheless, it turns out that if you work on this and think about it for long enough, I spent a lot of time doing this, but you can find a solution for this. You can find a zero energy solution to this equation that looks in this way. It's written in terms of an error function, and it is not very, what is the word? It's not very illuminating, really. I will show you a plot in the next slide, which will hopefully help us to see what this story looks like. But the really important thing is that at late times, this function qualitatively has a length-dependent equilibration rate, and I can compute that. Now let me show you those plots in the appropriate units where everything is set to 1. This is how the function looks like, and if you zoom in around this region, this is the behavior of the function. So as time goes by, as you can see in these colors, the function becomes, the fluctuation is being pushed towards smaller lengths, and its amplitude becomes smaller and smaller with precisely that length dependent rate I was mentioning before. And this is, you can see this equation. It's very nice to have an analytic expression for it, but it's very complicated. And this was the simplest case. So it could be difficult to argue that more complicated cases with finite d, with a number of non-compact directions, will admit this sort of treatment. So we would like to be more, to have a different way to address this. And we can have a very good qualitative understanding of what's going on actually from the intuition we get from this exercise. Why? Because as I was saying, the late time behavior of the fluctuation is this sort of decaying exponential with a length dependent rate. And this can actually be very simply read off the equation from the linearized equation. The decay rate is whatever is proportional to delta n. And this contribution is a spreading term that is going to make the fluctuation move around, but overall, the fluctuation decays with this rate. And reading off this term is something that I can actually do for all the more complicated cases. So for instance, let me show you how the calibration rates look like in higher D. And we can, of course, do this with in more complicated setups, right? We can also introduce open strings and estimate rates, estimate also rates of transfers of energy. If you are interested, I refer you to the paper. We did all of these computations. But what is nice is that we can infer, we can calculate, or we can do a very good estimate of what the equilibration rate looks like, which is precisely what you need if you want to compare, if you want to know whether a system is in equilibrium in an expanding universe. You need to compute the expansion rate H over this equilibration rate. So this is in my opinion, a great deal of progress if we want to set up to study Boltzmann equations to study string thermodynamics, sorry, in an expanding background, which is work in progress, as I was saying. But with this, let me just conclude. A brief recap: we have described the string thermodynamics in terms of what the typical macroscopic string looks like, and it looks like a random walk, and is very well described only by its length and the number of non-compact directions. Now, the equilibrium conditions that we have found, they agree with general equilibrium considerations, as we were saying before. And this is a very good consistency check of the interaction rates we've argued for. Because remember, all interaction rates must be written so that they satisfy detailed balance. And this is something we didn't impose from the beginning. We used random walk arguments to infer what was the rate. And then we check that they satisfy detailed balance. And lastly, presumably more importantly, we've been able to prove the out of equilibrium regime, and we've shown explicitly what is the behavior of fluctuations in very simple cases. And in general, we've managed to compute its equilibration rates. Many open questions remain. How can we do this in more complicated backgrounds? How can I take into account the self-gravity of the string? How can I take, I don't know, winding models? Can we say anything about the Brandenberger-Buffer argument for the dimensionality of non-compact space? This all can be studied. For the moment, what we are thinking of is, can this have left a gravitational wave imprint? And yeah, I think that's all I want to say. Thanks very much for listening, and I will be happy to take any questions.
Yeah, so I have a question. I thought I had the question. Yeah, so there were some old papers by Susskind on like what does a string look like when it gets close to the black hole? And somehow he seemed to say, if I remember things correctly, I might remember everything completely in the wrong way, but somehow he said that the length of the string increases if you look at it in a shorter time. So it didn't seem from his kind of arguments that the length of the string is a good quantum number. So that it was a bit surprising for me that it seems like this is something which is you can define and it's conserved in interactions and so on. So I don't know. It's not really a fair question, I guess, because this is something that you haven't thought of. But do you have any comment on that?
I think I can say something. I can hide myself in how I've defined length, which is in this way. And I don't know if this is how Susskind defined it, but this is in principle an invariant. If I assume that mu is fixed, the number of oscillators and KK and winding modes, in principle, is a quantity that I can talk about. Hopefully. But I am not sure with these papers of Susskind. I have not read them, but I would love to have a reference.
Yeah, it's a long time ago. I'll try to see if I can find something. I could send you the reference, but somehow, if I remember correctly, the sort of the sampling time was important.
I see. No, that's very interesting. I'd be happy to hear about it.
But it's to do with the black hole back, because this is a flat space, right? So
Right.
So in effect from putting it in a black hole back.
Yeah, that's a question. If if the black hole was causing this, but I somehow thought this was separate from the black hole, but indeed it was this thing that when he talks about the string getting close to the black hole, it sort of sweeps out and creates the whole horizon. It sort of spreads out on the whole horizon, the string, when it gets close to the black hole. But I don't remember if the effect was happened only close to the black hole, or you could also see it in flat space by changing the sampling time somehow. Yeah, I would have to find the reference, but the question came up when I heard you talk.
I see. Thanks for the nice question. It sounds very interesting.
How would you do physics if the string length is varying? Like, how would you even, I don't know, how would you write corrections to the action or anything like alpha prime corrections or like, I can't imagine a theory where you have the string length and this is varying. How would you do the theory? I mean,
it's a quantum effect. You can sort of, this real string is a sum over all possible types of string or configurations of the string. So you have a starting point, you have an end point, something in between.
But when we're doing physics, we fix the string length and then try to do.
What do you mean by the string length? If it's alpha prime, that's a different thing. Right? Square root of alpha prime is also something called the string length.
Yeah.
But that's not what we're talking about. We're talking about the length of the actual string,
Okay.
which of course can differ. You can sort of make a string of pieces in the way that Thorne did, and then the string you can add pieces and take away pieces, and the string gets longer or shorter. So the actual length of the string is something measured using string length as a basic unit, but it can of course change, and the string can become bigger or smaller.
You can see that from here, actually. No, if I have one unit of winding, then the length of the string, if you forget about this factor, is going to be proportional to the radius, which kind of makes sense, right? If you have a string winding a cycle and you make the cycle very big, then the string wrapping around that cycle must be big, right?
Yeah, that's a good way of putting it.
But is this related to the metric, the fact that it changes the length, or more about gauge?
Which gauge?
I don't know, if you take a theory with some symmetry and so on, and you can fix a gauge, and according to the gauge, it changes also the quantum number of the length. I mean, how can you say that the length is not a good quantum number?
Please don't take that statement too literally. This is something that I sort of remember from some papers that I read like 30 years ago. So I'm not prepared to defend anything I said. Just something that I sort of remember and was interested in hearing if there was some kind of effect of that sort in this game.
Okay.
I also have one question, so I'll just get closer so you can hear. So about this dependence on the small d and non-compact and compact directions. So you in your talk you introduced this typical string where you sum over all the winding modes and all sort of this typical string cannot see how many compact dimensions there are, right? So when in your calculation do you get back the dependence on this small d? Like from the definition of the typical string, it seems like you forget about how many dimensions you are, but then in your formulas, you always have this dependence on how many compact and non-compact you have.
Yeah. So how that comes by is that in here you need to perform this sum, right? In particular, among initial states of the string. And this is a sum into all possible strings that the initial string could be in. If, you know, this trace factorizes into oscillators and KK modes, right? And winding and this sort of story. If you are concerned about the dimensionality of the space-time and the, you know, critical dimension and all that story, that part is fine. It appears in the trace in the oscillators, and you know, you trace them, get a result, and how the little d shows up depends on along how many directions you've integrated winding numbers. If I say I have little d effectively non-compact directions, and I integrate over winding over all of the other ones, then my little d shows up here.
Yeah.
So you also said you would explain the factors that you had in the Boltzmann equation with the pluses and the minuses. That's something that I didn't understand. It seemed interesting. What's the difference? Why plus and minus?
These ones?
Right.
Ah, I see. They are quantum enhancement. So, you know, the minus.
Yeah.
So this has to be thought of as a probability, right?
Yeah.
Imagine imagine B is a fermion, and the particular state that, you know, this interaction leads to is a state that is already occupied.
I see.
Then the probability of decay is 0.
Okay.
Because of Pauli blocking.
So in your case, you were doing bosonic strings. So there is no pluses or minuses to take care of.
Yeah, plus I'm doing very semi-classical things, right? So, you know, sorry, where did I go? You know, what the pluses or minuses buy for you is including quantum effects, which in particular for bosons are not going to be very relevant.
Right.
But anyways, if E is very large, sorry, you know, if this exponential is large,
Yep.
then what I get is a Boltzmann suppression, right? Which is the sort of classical version of things. And we are doing, so if you want Boltzmann equations for a classical set of strings whose interaction have been quantum mechanically computed, you could write this. you could in principle write this, but it's not very clear because I'm not working with this momenta of, this is the phase space distribution. And for what I've posed Boltzmann equations for is for its first momentum. So it's this integral over all of these other parts of the phase space, and I've only kept the length. So when we started, I wanted to do this, but I'm not sure how to do it. So in the end, what I find is a Boltzmann distribution. Plus, if I may just make a comment, if it's in neglecting further contributions to this equation that I lose quantum effects. And the reason why I know this is that Amati and Russo in this paper computed the whole story. They didn't truncate, they computed the whole rate and found that a typical string radiates like a black body at the Hagedorn temperature. It radiates massless fields like a black body at the Hagedorn temperature. And if you do the same computations and do not take into account this, if you truncate, you get a sort of Boltzmann distribution for the decay products, as far as I remember. But all of that discussion is in this paper of mine, so I strongly recommend it. But yeah, the reason why I didn't include plus or minus, that those plus minus terms is that I wasn't sure how to, and it doesn't seem to be super important at this level.
Right. Right. Okay. Thank you.
Thanks.
I had one question. Can you go to the conclusion slide? The last.
Yes.
So your very last point. So you're looking, this phase we're talking about, in the cosmological evolution, what phase of the universe is it? It's after inflation. I think it's very similar to Giacomo's question. So it's after inflation.
It depends. It depends on what you are doing. In principle, you could have, and there is a very recent paper by Scott Watson and friends in which they study a Hagedorn phase as the initial conditions for inflation. So you could have that. Now, because my interest is in studying gravitational wave backgrounds, and inflation will dilute any sort of any such background, I want to study the Hagedorn phase after inflation.
Okay.
But in principle, there is no assumption of that in here.
So you could have this even after the brain-anti-brain inflation that you were talking about.
Sorry?
You could have this even after the brain-anti-brain inflation.
Very good. Very good.
Again, the scale is much lower than the string scale, right?
Not necessarily.
But in brain-anti-brain, we're looking much lower than the string scale.
You're looking at H much smaller than the string scale.
Yes.
So you're neglecting H, but remember that the Friedman equation tells you that rho is H squared times m Planck squared.
Yes.
If I want to make H smaller than the string scale, I only need to make H squared, rho smaller than m string squared and Planck squared.
Yeah.
But if there is a big hierarchy between the Planck scale and the string scale,
Yeah.
you are allowed a very long range of energy densities between, ms squared and Planck squared and m string to the fourth. There is a factor of, m string over m Planck squared that the other way around that you can write, that you can access without worrying for alpha prime corrections. In principle, what is measuring the strength is H. And the key of the story is that there H as in a Hubble parameter, right?
Yeah.
Because H controls the curvature of the spacetime.
And you could in principle have these gravitational waves from the fluctuations.
Sorry?
So you could have this gravitational waves from the fluctuations.
Or from the decay product.
Oh, okay.
It could be any of those. It could be any of those. But the good thing about this is that these guys decay into gravitons, into massless field, into gauge fields as well. If you have branes, no, or if you have, I mean, it will decay into everything, and that's why I think this can have some words on the moduli problem. But that's a different story. But yes, in principle, these guys decay into gravitons. So if there is sufficient amount of gravitons, there might be a gravitational wave spectrum, which is of course bounded by Big Bang nucleosynthesis. No, its amount of energy density is bounded, but that's a different story. For which I strongly refer you to that to this paper. Let me just do a little bit of advertising. This paper. People are getting very interested in this.
Yeah.
And the reason is that, if we want to see the early universe, in which of course there were the highest energies, if we want to use a telescope, I cannot look farther than the CMB, than the last scattering surface.
Yes.
But there is no such scattering surface for gravitons.
Exactly. Yes.
So gravitational waves, if you are able to measure these gravitational waves, which they are proving very different, very difficult to even think of a detector, but if you could, you will have the highest energy laboratory in the existence of nature, which was the early universe. So it's very promising.
Okay, do we have more questions? Well, let's thank the speaker once again.
Thanks.
Thank you very much. I'll stop the recording.
My pleasure. My pleasure. I hope to see you all soon.
See you, I think, next week.